Right. So before that, before entering into the subject, we have to know what is the PVT surface. Right. So each and every substances will have this PVT surface that under the state, the substance will have the pressure, will have its own volume, and will have its own temperature. So at any stage, the pressure, temperature, and volume to be considered to get the PVT surface of the substance. So the pressure can be expressed as a function of a temperature and a specific volume. That can be P will be a function of temperature and volume, the specific volume. Right. So the plot of pressure is a surface called PVT surface. Then this figure will show you the PVT surface of the substance such as water that expands for freezing. So we can have all the substances with this PVT surface diagram. Then for an example, we can take the water, then we can consider the PVT diagram of water. So this axis, this y-axis will give you the pressure column. Then this specific volume is taken in this x-axis. Then we can take the temperature in z-axis. Just if you consider, we can get this PVT surface diagram. Then also we can take, this is a 3D diagram. So if you want to take the 2D diagram, we can separate this 3D diagram into two. So we can take the pressure and temperature. So if you look the pressure and temperature line, so we can have to look from this. So I think you study the engineering graphics. So just if you want to the 2D diagram of this 3D diagram, just the parameter pressure and temperature, just we have to look from this. So if you look like this, then we can get the properties of water with these lines. So there will be a solid phase, then there will be a liquid phase, then there will be a vapor phase. Right. So this point will be a triple point. This point will be a triple point, and this point will be a critical point of any substances. So then this phase, solid liquid region, solid liquid line. Then this phase is a liquid and vapor line. Then this phase is a solid and vapor line. So at this point, we can get the triple point of a substance. So like that, we can take the 2D diagram of our pressure and a specific volume. Just again, yes. Sorry, that first figure will be seen from this view, and the second figure, pressure and a specific volume figure, will be taken from this view. So we can get this view. So I think we know this. What is the diagram? PV diagram of our pure substances. So in that PV diagram, we have the saturated liquid line. This one is the saturated liquid line, and this one is the saturated vapor line that you know very well. Then this one is your this line. This line is your mixture line, right? So in this region, the substance will be the mixture of two states like liquid and vapor. So we can call this as a mixer for a pure substance, right? So below this, the temperature below this saturation liquid line is low, means we can say that the substance is in subcute liquid. Then if the temperature above this saturation vapor line is the temperature of a substance, we can tell that the substance is in superheated region. So that you know very well. So we no need to discuss more about that. So the thing is, we have to move. We have to see this separately for water. Right. So this is the PVT surface of a substances. So these three diagram can be used for identification of the properties of the matters or substances. Right. So the location of a point on the PVT surface gives a values pressure, specific volume and temperature at equilibrium. The regions on PVT surface labeled solid, liquid and vapors are single phase regions that you know very well. The state of a single phase is determined by any two of the properties that you know what is phase. So we have to consider the any two properties, then we can get this phase. Then if for an example pressure, temperature and specific volume can be taken accordingly. Then the two phase regions where two phases exist in equilibrium separate in a single phase region. So we can also get the two phase region inside single phase region. Then two phase regions are liquid vapor region, then solid liquid region, then solid vapor region that you know. And the temperature and pressure are dependent with the two phase regions. Once the temperature is specified, the pressure is determined and vice versa. Then the states within two phase regions can be fixed by specific volume and either temperature or pressure. So we can determine the two phase of the region with these three parameters. Then the projection of a PVT surface onto a PT plane is known as the phase diagram. Right. So PT diagram is called as a phase diagram. Then the two phase regions of a PVT surface reduce to lines in the phase diagram. That line, the two phase region will be on the lines of the PT diagram. A point on any of these lines can represent any two phase mixture at that particular temperature and pressure. Right. So the triple line of a PVT surface projects onto a point on the phase diagram called a triple point that you know very well. So each and every substances will have this triple point. So there are three phases coexist on the triple line or the triple point. So with this introduction, yes, we can move to the topic properties of steams. So in these slides we have these introductions, then constant pressure, formation of steam, then different curves for the formation of steams, then characteristics of steams, then various processes for steams, and the determination of Riemann factor for a steam. So will be discussed in this PowerPoint presentation. Then introduction about the steam. The steam may be defined as a water vapor suspended in air that you know very well. So it can be classified in wet, saturated, or superheated. Then vapors may be considered as a fluid in gaseous state as it may contain liquid particles and its temperatures is not far from its boiling point that you know very well. Just steam, right? So we have the steam in these three stages, that is wet steam available, then saturated steam available, then superheated steam available. Right. So you know what is subcooled liquid. That subcooled liquid of steam can be called as wet steam. Then you know what is superheated vapor. That superheated vapor is called superheated steam here. Then you know mixer. That mixture is called saturated steam here. Right. So the vapors may be considered as a fluid in a gaseous state as it may contain liquid particles and its temperature is not far from its boiling point that you know very well. So the wet steam do not obeys gas law. Why? So actually wet steam is a subcooled liquid, right? So liquid won't follow the gas law of Boyle's and Charles. So it's not pure gas, right? Then so it is produced by heating of water that you know very well and carries large quantity of heat within itself. Hence it could be used as a working substance for the heat engines and the steam turbines. So where we use the steams, we will use the steam in heat engines and the steam turbines also. So that you know what is heat engines where we are using, and what you know what is a steam turbine where we are using. So this is our example of a heat engine. Then this is example of steam turbines. So in olden days, rails engines were run by the steam turbines. Right. So this is the procedure for producing the steams with a constant pressure formation. Then, so just if you follow this diagram, yes, we can produce the steam. So steam is generated in boilers. So the main component of the formation of steam is storing of steam is boiler, right? So you know, a lot of mechanical companies like Bell's BHEL were producing these boilers. So it should be very specified one. Right, so consider a unit of mass of ice at 20 degrees Celsius and 1 atmospheric pressure contained in a cylinder piston system. So like boiler. So let the ice be heated slowly so that it's will follow this figure. Right, so consider in a piston cylinder, uh, we have 1 kg of ice with 1 atmospheric pressure. This weight is given to maintain the pressure at 1 atmospheric pressure, right? So also we can this system is closed system. We can transfer heat energy into the system. So if you provide heat energy into the system, we can get these changes. So we will look at that one by one. I think there is no explanation. Yes, I will explain. Right. So if you add heat to this ice, what will happen? Just this ice will try to melt, right? So this solid phase will transfer into liquid phase. Then if you keep on adding heat energy into the system, the water gets saturated water, right? So some amount of heat energy will be absorbed by the water. Then the water is transferred as saturated water. Then during this saturation process, the volume of this water will be increased, right? The specific volume of the water will be increased. Then after, if you keep on adding again heat energy to the system, the saturated water will try to produce steams, that is wet steams. Wet steam in the sense there will be some moistures in that. So the wet stream will form. Again, if you wet stream also, there will be some amount of water inside that. So if again if you keep on adding the system temperature to the system, the whole the water will be converted into a wet steam. So again there will be a increase in our specific volume. Then again if you keep on adding the temperature, so the wet steam will be converted into dry saturated steam. So the wet portions, the humidity of this wet steam will be dried, and we can get the dry saturated steam. Also this will get the increased specific volume. Then if you keep on adding the temperature, finally we can get the superheated steam. The steams used in the gas turbines, steam turbines is superheated steam. So in some other case we may use the wet steam and dry saturated steams also. So depending on that, we have to know the properties of the steams. So this is the process of constant pressure formation of steam. Then we can produce the steam with the pressure constant by the addition of heating, right? So this is the phase changes. So the phase changes can be obtained from the pH diagram of the steam. So this is your TH diagram, that you know temperature and enthalpy. So just you can this. So if you enthalpy in the sense heat content, right? So yes, if you keep on adding the temperature, yes, we can get this heat content. So for an example, the heat and content should be increased. So from 0.1 to, this is ice state, and from 0.1 to 2 there will be a increased heat content. Again, during melting of ice, we can get the constant heat content. Then again, during solid phase to liquid phase, during saturation process, we can have the increased heat content. Again, during vaporizing process, you know what is vaporizing process? The saturated liquid gets vapor, right? So during that process, we can have the constant heat content. Then after the saturated vapor, we can get the superheated steam. In that region, we will get the increased uh, heat content. So, so if you increase the temperature, we can get the increased heat content. So the process is reversible. The process is reversible. So if you reduce the temperature, so if you take a superheated steam, then reduce the temperature, then the process will be reversed like this. Again, the process will be reversed like this. Then the final temperature of ice will be reached. Right. So we can so during forward motion there will be a melting and vaporizing. During reverse motion there will be a condensing. Okay, so if you want a superheated vapor into saturated liquid, we have to condense that. Then if you want to saturated liquid with ice, means we have to freeze that. If you want to, this is liquid, right? So this is liquid. If you want to liquid to ice, means we have to freeze that you know very well. So these are the TH diagram of the steam. Then the heat, the latent heat of fusion is in this region, that you know what is fusion. Then sensible heat of liquid in this region, to be in this region. Then latent heat of vaporization is in this region. Then sensible heat of vapor is in this region. So from this TH diagram, we can identify the heat content of the steam. Then we can classify the regions. Then we have the TV diagram of the phase steam, that you know temperature and your specific volume or specific volume. So the same process. If you consider the temperature and specific volume, the in this region, that you know ice region, right? So the volume increases from V1 to V2 as the ice temperature is increases to 0 degree Celsius. That you know, so minus 20 degree Celsius temperatures is reduced to 0 degree Celsius, but the volume of this process is gets increased. Then the second process, you know very well, that the solid state to liquid state, right? So solid state to liquid state, again the volume of this water in this region gets decreased. Then the volume of in the third step, that you know liquid to saturation liquid. So the volume of the water slightly decreases, right? So from 0 degree Celsius to 4 degree Celsius, right? This is 4 degree Celsius. Then again in the next process is in the next process, that from saturation liquid to superheated saturated vapor. So in this process, the volume of water gets increased due to thermal expansion, right? So in the fourth and fifth process, again saturated liquid to superheated, I think. Yes. So in this region, there is a large increase in volume of water due to formation of steam. And finally, we can get the superheated steam with the increased volume. Right. So this is a TV diagram. So the same process. For this process, we can get the TH diagram. Also, we can compare the TV diagram. During the phase changes, we can get the increased or decreased volumes. Then we can have the PV diagram of that process, PV diagram of our steam. So you know, this is your saturation liquid line, then this is your saturation vapor line, that you know very well. So this is your critical point. Then this is your mixture and the mixture of liquid and vapor, that you know. Then in this region there will be a the temperature, if you consider, there will be a substituted liquid, then superheated region, that you know very well. So here we are considering the pressure and volume. So pressure of this steam will be increased, will be like this. So for an example, take this one, this curve. So at this point there is a liquid saturation curve, right? So so this region is our mixer region, then this region is a superheated steam region, then this is your wet steam region, right? So this is your isotherm, this is your isotherm. Then we can have the temperature ranges here, so this will be some temperature, then this line will be some temperature, then this line will be some temperature, so this line will be some temperature. So actually we can take only the PV diagram of this, and also if you want we can take the isotherm also, that is temperature. Then so this is your TS diagram. So this is what we discussed earlier. So TS diagram. So in this TS diagram, just listen this one. So the saturation liquid line will be like this. Then the saturation vapor line will be downs compared with the saturation liquid line. Right. So this line will be your triple point line. So the triple point can be exist in this point. So this is your solid region, solid plus vapor region. So this is your vapor region, then this is your mixture region, that is liquid plus vapor region, then this is your liquid region, this is your solid region, right? So just we have to know, this is solid region, this is liquid region, then this is vapor region, this is vapor region. Then we can get the triple point here, so we can get the two phase systems, yes, whatever you want, right? So this region will be your subcooled liquid, then mixer, then saturated region, right? So then also we have these for steam, we can have this TS diagram, so that you know very well. So this point will be critical temperature, critical point. For steam, we can have the critical temperature as at 374.15 degrees Celsius. Then these lines will be pressure lines, that you know. So these lines will be pressure line. So from these graphs we can get the properties of the steams. Then we can define the properties of steam. The main properties of steam is enthalpy, the total heat of water, that you know, HF. So HF stands for enthalpy of water, fluid, right? So it is defined as the quantity of a heat required to raise the temperature of 1 kg of water from 0 degree Celsius to its boiling point, or saturation temperature corresponding to the pressure applied. So it is also called the enthalpy of a saturated water or liquid heat, and it is represented by HF. You know that HF can be calculated, that is your specific heat of the water, that is your constant pressure heat, specific heat at constant pressure for water into change in temperature, that you know the formula of HA. So H can be calculated with this formula and can be defined like this. So to increase the temperature, right, heat required to increase the temperature of 1 kg of substance to 0 degrees Celsius to boiling point. So that you know the specific heat of water at constant pressure will be 4.187, that can be taken from our property tables. then the change in temperature. So if you want the enthalpy of water or total heat of water, you can calculate that if you know the temperature difference. Then the next properties of steam is enthalpy of wet steam. So here in the case, this is water, enthalpy of water, that you know. Then this is for wet steam, that is mixture. Sorry, yes. It may be defined as the quantity of heat required to convert 1 kg of water at 0 degree Celsius at constant pressure into a wet steam. That you know, wet steam. So again, the formula will be H is equal to HF plus X into HFG. So this formula you know very well. So when a steam is dry saturated, then your X will be 1, right? So then only we can get the wet steam. Then we can have the equation as HF H is equal to HF plus X into HFG. The same equation, no need to confuse. We can neglect this one. So if X is 1, we can have the equation H is equal to HF plus HFG, right? Then the third property, latent heat of steam. So enthalpy of steam can be calculated. So latent heat of steam at a particular pressure may be defined as the quantity of it's required to convert 1 kg of water at its boiling point into dry steam. That is where after the saturation state. At the steam pressure, it is denoted as HFG. That you know, this is a latent heat of your steam. HFG. That you know, HFG can be calculated with the Hg minus HF. Then you know what is X quantity for pure substance, but fraction for steams. So X can be called with the name dryness fraction for steams, right? So this dryness fraction is defined as the ratio mass of a dry steam actually present to the mass of wet steam, right? We can take the ratio with the dry steam and the wet steam, and this is denoted by X. Also you know what is ms and what is mw, mass of dry steam, then mw, mass of water vapor in steam. Then X will give you the dryness fraction of the sample. Then that X can be called by the formula X is equal to ms by total mass. Mass of the steam divided by total mass. Then if mw is equal to 0 and X is equal to 1, that is for dry steam. So in that dry steam there is no moisture, right? So we can the saturation superheated region. So in that region we can have the this dry point on the saturation vapor line. So there will be X is equal to 1 and there is no water mw there. This dry steam will occur on the saturation vapor line, right? So on that point we can have the mw 0 and X 1. So finally we can have the equation as ms, right? So the quality of a steam is dryness fraction expressed as a percentage. That you know, normally we will express the quality in percentage. Here for steam, dryness fraction also will be in percentage. Then the wetness fraction, the opposite of your dryness fraction will be 1 minus X. That can be calculated by mw by total mass. Then this wetness fraction expressed in percentage is called priming. Okay, so we can have the dryness fraction, also we can have the wetness fraction. So if the steam is in dry steam, we can get the dryness fractions. So if a mixture of your wet steam and dry steam, we can get the dryness fraction and wetness fraction. If you want to calculate the priming, you have to found the opposite of your dryness fraction, that is called the wetness fraction. Then the next properties is the enthalpy of a superheated steam, right? So that you know what is superheated steam. So the specific heat that CPS is a specific heat at constant pressure for superheated steam denoted like that. Then this TS again temperature of formation of steam, that is saturation T, and again this T SUP will denoted for a temperature of superheated heat. It will be in degree Celsius. Then we can calculate the heat of superheated steam with this equation. H is equal to Cp delta T. Cp delta T. So here H superheated can be calculated as CPS, that is saturated, minus change in temperature, that is superheated temperature minus saturated temperature. If you want to find the total enthalpy, means we can have all the that is our H saturation, normal H plus this superheated H. So this can be substituted in this. So this can be substituted in this. That normally we know H is equal to HF plus X into HFG. But in the case of superheater, we don't have X, that you know very well. Then if you want that superheated H, then we have to add this also. The formula will be HF plus HFG plus Cp into change in temperature, right? So this, so if you implement this HFG, so we will have this HG minus HF, right? So HG minus HF in this. So here is plus HF, and here is minus HF. Then these two will cancel, and finally we can have the equation as Hg plus Cps into change in temperature, right? So this is the equation for the superheated H entropy. Then in actual practice, it is quite cumbersome to calculate the relation between various quantities like pressure, temperature, volume, enthalpy, latent heat, and entropies of steam, right? So such quantities have been determined experimentally and recorded in the form of tables, that is called our steam table, right? So we can say the property tables in the name of steam tables if the properties is particularly for the steam, right? So we can call the tables called steam tables that will have the properties of steams like pressure, temperature, all the other thermodynamic properties of the steam. Then the value of various quantities given in these tables are for a kg of steam, or 1 kg of steam which is dry and saturated. The value for unknown pressure or temperature can be calculated by linear interpolation between two consecutive values, like our what we did in early. So the same, but we have to consider steam alone. So steam table can be taken to get the properties of the steams. Then the specific volume of wet steam, that can be calculated, that you know Vg. The specific volume of steam is the volume of 1 kg of dry steam, and it is represented by the name Vg in the unit meter cube per kg. Then the density of our steam, that you know density is equal to mass by volume, right? Density rho is equal to mass by volume, that we know very well. V by m equal to small v, right? So that is inverse of your specific volume, right? So the density equal to inverse of your small v, that was stated here. Then that you know Vf, the volume of 1 kg of water, that is specific volume of fluid, liquid, water. Then the volume of 1 kg of wet steam can be calculated with this equation, that is your x into Vg plus that is Vg for x for Vg gas, that is your wet steam. Then this dryness fraction, wetness fraction for your fluid, liquid, water. Right. So if you add both together, we can get the volume of 1 kg of wet steam. So if you compare these two, the volume of with the wet steam specific volume will be a hugely more, right? So volume of your uh, water will be, specific volume will be very less. Then we can neglect that. Then we can have the volume of 1 kg of wet steam will be x into Vg. So the density of our wet steam can be replaced as, that is, that 1 by Vg. So this 1 by Vg can be replaced for wet steam as 1 by x into Vg. Right. So density for your steam is actually 1 by Vg, where in the case of wet steam, the density will be 1 by x into Vg, because we have x in the wet steam. Then the volume of superheated steam at a given pressure can be found by assuming the superheated steam behaves as a perfect gas. That superheated steam will be like gas, that will obey the gas law. So we know PV is equal to constant, PV is equal to MRT formula. So that can be taken accordingly. So the Charles law will be like this. So V by T. So the terms V and T can be taken. So V by T superheated, V superheated by T superheated will be equal to Vg by Ts. Same. Here for G stands gas, that here Ts stands temperature of your steam. Right. So this is the formula for your specific volume of superheated steam. Then we can have the various processes of steams. So we can have the constant volume process, that how the constant volume process. The constant volume heating process is shown in PV and TS diagram in this. So this is PV diagram. So in this is constant volume process, right? So if the process is constant volume, the change in volume will be 0, right? From process 1 to 2, then process 2 to 3. Just if you compare, there is no change in specific volume. So if that specific volume, change in specific volume is 0, we can get the change in work done as 0. That very well. So area under the curve will give you the PV, the area under the PV diagram will give you the work done. So there is no work done in this constant volume process. Then finally we can have the equation for T capacity. Q is equal to change in internal energy, that is U2 minus U1. Then from this will give you the TS diagram. So temperature, the entropy will change, right? So during this constant volume process, the entropy will get increased from the process 1 to 3, right? So the area under this TS diagram can be your Q, right? So then we have the constant pressure process. So if the process is constant pressure, that we know this is constant pressure from the PV diagram. So there will be some area. So definitely there will be some work. Then that work can be calculated by integration of PdV. So here P is constant. So the latent heat of steam and specific volume will remain same. That Vg1 equal to Vg2 equal to Vg. right? So here we have compared two states. So Vg1 is equal to Vg2 is equal to same, that is Vg, and also we have Vfg1 equal to Vfg2, sorry, Hfg2 equal to Hfg, right? So then we can have the Q as x1 minus x2 into Hfg for wet steam. Then Q is equal to H superheated minus that Hfg can be multiplied, right? Hs minus Hs, H superheated minus H saturated, right? H superheated minus H saturated. Then for isothermal process, so this is your PV diagram of our isothermal process. So isothermal in the sense is in a constant isotherm. So in a constant isotherm, that the isothermal line will be like this, right? So the isothermal heating process shown in this figure, the isothermal process for wet steam will be same as the constant pressure process. Just if you compare the isothermal process and the PV diagram of this will be same as a isobaric process, but in the superheated region the steam will be behave as a gas, right? So after this superheated region the steam will be behave as a gas, so we can have the increased PV is equal to constant, so we can get the increased pressure, right? So we can have the equation Q is equal to H2 minus H1, and we know, so if there is Q, we can get the W as a P1 V1 into 1 minus X1, that is your wetness fraction. So this is your TS diagram. So after in this TS diagram there will be a curve, right? Then this curve after the superheated region is called hyperbolic process. That can be defined during a hyperbolic process. Your PV is equal to constant, that is obeys the gas law. The process may be regarded isothermal, but only in the superheated region. So in this region alone we can get this hyperbolic process, that a change in internal energy can be calculated in this region by U2 minus U1, that is your H2 into x2 into P2 V2. Again H1 is equal, that is H1 minus x1 into P1 V1, right? So that can be reduced, so we can cancel. So for wet steam there is no other values, so these values can be omitted for wet steam. Actually this is for saturated steam, then this equation for wet steam. Then we can have the work done will be calculated by using this formula, that is your P1 V1 ln V2 by V1, that plus P1 x1 Vg1 into ln V2 by V1. So just we have to use the formulas from the thermodynamic processes, then we can get these formulas. Just remember these formulas. Then we have another process, that is a reversible adiabatic process, that isentropic process. So isentropic process of steam is compared here from this TS diagram. So this TS diagram. So let the steam be expanded from state 1 to 2. So this was expanding, steam is expanding, then we can get this TS diagram. Then we can calculate this x2. So this, there was some derivation. Just if you want, I will derive that. Just wait a minute. Just there is some derivation, right? So Right. For superheated steam, we can have this Q is equal to 0 and W is equal to U1 minus U2. That is U1. This is the value for U1. That you know the U1 equal to SF1 plus HFG1 divided by, this can be written as SFG. SFG entropy. So here for wet steam, S1 is equal to S2. Wait, I will derive that if you want. Then I will come that later. So just the thing is, we can have the x2 for wet steam with this equation. Then again we have polytropic process. That you know, a polytropic process is a thermodynamic process that obeys the relation PV power n is equal to constant, where P is the pressure, V is the specific volume, and N is the polytropic index. Is any real number and C is a constant, that you know. This equation can be used to accurately characterize processes of certain systems, notably the compression or expansion, including with the heat transfer of gas and in some cases liquids and solids. So finally we can get the W as a P1 V1 X1 minus P2 V2 X2 divided by, that is you know, for polytropic process, PV power n is equal to constant. So here n minus 1, that you know, this formula PV change in PV divided by n minus 1. Then we can have the Q as W plus U2 minus U1, where n is equal to 1.13 for wet steam and 1.3 for superheated steam. Right. Then we can have the equation as P1 X1 Vg1 power n equal to P2 V2 power n. Right. To derive this, I will use your smart board. Just I will derive that. Yes. So you know, S1 equal to S2. That S can be written as S is equal to SCF plus F into SFG, right? So this SFG can be written as SCF plus X into you can read that, right? So if S1 can be written as SF1 plus X into X1 into XG1. If you want X2, we can write SF2 and X2 into SFG. Right. So we know S1 is equal to S2, so we can write that S F1 plus X1 into SFG1 equal to S2 plus X2 into SFG. This S2 stands F as a right, so this is SFG. So we need to keep X2 from one side. So this will come here. We can have a CF1 minus SF2 plus X1 into SFG1. So we have in multiplication then you have to take into denomination, that will be your 1 by S F 2, right? So we can have, so if you want x2, you can write the equation as SF2, the SF1 minus SF2 plus this is x1 into SFG can be written like this. You know, S is equal to HVT, so we can write like that. So here we have SFG in inverse, so we have to invert that. So HFG divided by TS2. So that is the derivation of this equation. Just try to remember that. Then this is polytropic process. Then for throttling process, we have the TS diagram. So throttling is a process that you know, in which the following the flow of fluid is restricted by closing the valve partially. Now imagine there are students in a classroom, and as bells rings, they started moving out. So just this is the imagination for the throttling process. So what will happen? So now if the door is open partially, then there will be a cluster formed by the student. So in flow of fluids, there is a restriction to flow. So now as students from cluster, they push the other students, and in the same way, fluid particles start rubbing with the other molecules. And as a result, friction is there. And as a friction is one of the biggest reason for any processes to make it irreversible. So why we introduce the throttling process? To get this irreversibility. So irreversibility may be caused by the frictional result of friction. Right. So this is your TS diagram of your throttling process. Then, so how can we determine the dryness fraction? So we have some experiments to calculate the X. So there are 4 methods to determine the dryness fraction of steam. So there is one is a barrel calorimeter, then we have separating calorimeter, then we have throttling calorimeter. We have combined of these separating and throttling calorimeter. So this barrel calorimeter, here a known amount of water is filled in the calorimeter. Then certain quantity of steam from the main pipe is taken into the calorimeter. Then steam and water mixed together, and so condensation of steam takes place. Right. So if you mix the water and steam, you can get the condensation of steam. Mass of water in the calorimeter increases. Right. So this latent and sensible heat of steam is given to water, and its temperature will increase. So just we will mix the steam and water together to get the increased temperature and other sensible heat. Right. So the amount of heat lost by steam will be equal to heat gained by the water and the calorimeter. So from that we can calculate this dryness fraction. X is equal to mW, is total mass, into CPV, that is specific heated constant pressure for water, then change in temperature minus mass of steam into specific heated constant pressure for steam into change in temperature divided by m into h. So from this equation we can calculate the dryness fraction of our steam with the use of barrel calorimeter. So this is the diagram of our barrel calorimeter. So just we have some water with a known value, then we will try to mix the steam with this, then there will be increased temperature. So from that we can calculate the dryness fraction with the use of this temperature, with the use of this equation. So we know the other values, CPW we know, then CPW, CPS we can take from the tables. steam tables, then we can found the X value with the use of barrel calorimeter. Then we have another method, separating calorimeter. So in this type of calorimeter, water particle from steam are separated first in the inner chamber and its mass can be measured. Right. So first we have to measure the mass of the water. Then the dry steam is then condensed in the barrel calorimeter as what we discussed in the early and then previous slide. So these two mass difference can be taken to calculate the dryness fraction. So this dryness fraction will be equal to the mass of your steam divided by total mass. So this there is some limitation in separating calorimeter. So limitation is that the approximate value of X is obtained from this, because the total separation of water particles from the steam is not possible by mechanical means. So to rectify that, so this is your separating calorimeter diagram. So all these three. So we have some mass of, we can calculate the mass of water. If you pass the steam through this, we can calculate the mass of the condensed steam with this balancing. So we can calculate the difference between the ratio of the masses to calculate the dryness fraction. Then we have the third, throttling process. So in this calorimeter, a throttling valve is used to throttle the steam. The steam pressure of the pressure of steam reduces after throttling. That you know, the pressure and temperature of a steam before and after throttling is measured here. Then the enthalpy of the steam before and after throttling remains constant. That you know, there is no change in enthalpy in the process throttling. To measure dryness fraction condition of steam after throttling must be superheated steam. Right. So if you want to found the dryness fraction in this throttling process, the steam and after the throttling process should be superheated steam. So the enthalpy of a steam before throttling will be equal to enthalpy of the steam after throttling. So also we have this limitation here. So steam must be become superheated after throttling, right? So then on that case only we can use this throttling process calorimeter. That means it is not very useful for steam containing more amount of water particles. So the X value should be above 70%. So if the X value should be above 70%, means we can use this calorimeter to calculate the X. Then this is the diagram. So we have the throttle valve here. So the steam is passed through this throttle valve. So we can have the enthalpy before and enthalpy after. Right. So this is get compared to get the dryness fraction. Right. So again we have the fourth one, combined separating and throttling calorimeter. So the limitation of separating and throttling calorimeters can be overcome. So you know, separating calorimeter we can have approximate value, and in throttling calorimeter there should be a superheated one. So if we compare both, we can get this calorimeter. So to overcome, if they are used in a series in this type calorimeter, so it's give accurate estimation of a dryness fraction that can be X is equal to X1 into X2. That X1 will be your H2 minus HF1 plus that we discussed earlier, right? So HF, this formula is already there, we discussed. Then HFG. Then we have this X2, we have this formula. So both formula will be multiplied to get the X of this calorimeter. Right, just a series of separating calorimeter and throttling calorimeter. So this is the diagram. So this is your separating. Yes, this is your separating. Water is separated, and then water and steam is steam mixture is separated. So this is your separated calorimeter. Then from this we can taken the steam to the throttling calorimeter. So here is the throttling valve. Then the combination of series of these two will give you the exact value of dryness fraction. So that is the thing. That is the properties of steam that can be used in steam turbines and or other engines. So the thing is, we have to use the properties of steam, right? So we have to know the properties of steam. So for the combustion of our properties, we have the steam tables. That steam tables can be referred in our property tables and chart. So in this syllabus we have steam table, so that you know very well what is interpolation, how can we use the steam tables and chart. So for that we will open that slide also. Just wait a minute, just refer the steam tables and property tables and chart files. Where it was, I think it was in unit 1. Yes, I think you can be able to see the property tables and chart. So the steam values can be, the steam tables is here. Yes, this one. Yes, saturated water temperature table is your steam table. Then saturated water pressure table also is your steam table. Then superheated water table A6 also your steam table. Then compressed liquid water also your steam table. Then saturated ice water vapor. Then TS diagram for water. Then Euler diagram for water. So where these are the properties of water. That can be water in the sense we can use the water as a steam, right? So these tables from A3 to A10 can be taken for the taken for the determination of properties of our steams, right? So these tables, so saturated pressure temperature will be there. Then we can have that, you know very well. So we can have the specific volume, then internal energy, enthalpy, then entropy, then you know what is HF, what is HG, and you know what is HFG. So from this steam table we can taken the temperature. Then if you want to found the 20, here we have 20 degrees Celsius properties. Then we have 25 degrees Celsius properties. And if you want to found these in between these values, like 23 degree Celsius, we have to use the linear interpolation, right? So that you know very well. Just we can use the steam tables to get the properties for steam as such. Then you know what is saturated water, then what is superheated water. So this is superheated steam actually, right? So we can take the properties of saturated superheated water as a superheated steam. That is your then we have continuation of superheated water. Yes, this one again continuation. Then we have A7 as compressed liquid water, right? So this is your compressed liquid water, that is your wet steam, right? That is your steam. So from that we can get the values like this. And then we have saturated ice water region, right? So we know what is saturated ice and water vapor region. That from we can use this table to calculate any other property we want. Then this is your just wait, I will teach. Yes. So this is your TS diagram of our water. Just we can we can compare the temperature and S of the entropy of our water. So this is your saturation liquid line, you know. This is your saturation vapor line, we know. This is your critical point, you know. Then these are some pressure lines. So see, can we zoom it? Yes, these are some. The 30 kg per meter cube is pressure, right? So these are pressure. Then we have X values also. So this is 30%, this is 20%, this is 10%, 40%, 50%, 60%, 70%, 80%, and 90, 100%. Right. So this is your TS diagram for water. That is can be referred for steam also. So this chart also can be used instead of your steam table. The thing is we have to use properly. So if they gave any temperature and see, for example, if they give 100 degrees Celsius temperature and your X is 50%, your X is X is 60%. If you want to determine the entropy, we can use this. So T is 100 degrees Celsius, and your in this 60% X, we have to take in the value of S. So the S value will be approximately 4.98 something kilojoule per kilogram Kelvin. So unit in kilojoules, right? Right. So this is a TS diagram. So for steam, also we can have the Euler chart, Euler diagram. So in this Euler diagram, actually, wait a minute. Right. So this is Euler diagram is S and H. S H diagram, enthalpy HS diagram. Right. H and S diagram can be called as Euler diagram. So this diagram has the enthalpy value in x-axis, the y-axis, and the entropy value in x-axis. So also we have some other pressure values. Then so these lines, these rose lines. So these lines, P is equal to 0 kg, P is equal to 0.01 bar. So these lines, this is pressure is equal to 10,000 bar. So these are the pressure line. Then these are the density lines. Then also we can have this. What is this? This is X. Right. So X lines were here. So these lines will be for quality. So 100%, 98%. This one is 100%. So actually, this is a saturation liquid line, and this is a saturation vapor line. This is your critical point. So also we have Euler chart that consists a TS diagram. Right. So these from these steam tables and charts, we can get the combustion properties of our steams. So we can refer that properties to calculate any other problems. Right. So you know very well these properties of steam is like our properties of pure substance. Just go through this. right? So that is enough. So we can move to the next portion of this third unit in the tomorrow class. So that's it from today's class. Yes, if you have any queries, you can wait and ask, or else you can hang up. Thank you. Have a good day.
Thank you, sir.
Thank you, sir.
Orange.